Well, greetings, mathletes, and welcome back. Today we're going to be talking about exponents. Now, we're getting ready for dealing with what's called polynomials, and so we have to understand how exponents work first. So we're going to go through and we're going to look at the rules of exponents. We're going to see where those rules come from and why they're the rules that they are, and then we're going to get a little experience working with those rules and see how they play out. So without further ado, let's go ahead and get started here. Okay, so the first rule we're going to look at isn't really a rule unto itself. It's really more the definition, and it's what we're going to be drawing. All of those other rules that we get are going to be basically consequences of this definition. And so, when we look at a problem, I'm just going to pull out the numbers here first. Let's say I have 4 to the 5th power, right? So that would be 4 times 4 times 4 times 4 times 4, and we have it there 5 times because the exponent is 5. And if you go ahead and compute that, you should get that 4 to the 5th is 1,024. You probably want to check. I'm pretty sure that's right. But and vocabulary first here. This 4 is the base. The 5 is the exponent. Wow, my handwriting's bad. The 1,024 is the power. I know a lot of the time the 5 would be called the power. And it's pretty forgivable, really, if you do say that, because 1,024 is the 5th power of 4. So, they kind of get used interchangeably, but if you're in a situation where you have to be technical, the answer you get is called a power, right? The exponent is the number that's sitting in a superscript over the base. Okay, just so we have that down. And then let's go ahead and get rid of that. And let's move this picture off my controls. There we go. Okay. Now, so for definition, right? We basically, in fact, I want to do this in a different color. Let's try this one more time. Okay. So as a definition, x to the n is equal to x times x dot 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 times x, and this happens n times. Right? So that's basically our definition. Now, the first rule that we often see is that x to the m times x to the n is equal to x to the m plus n. Now, what that means, basically, is if I have something like x to the third times x squared, what it does is it gives us a little shortcut to coming up with the answer. Because what's happening here is I have 3 x's multiplied here, and over here I have 2 more x's. And if we ask ourselves, how many x's are we actually multiplying here? There's 5 of them. So this is actually x to the 5th. Because what we do is we add the 3 that are being multiplied here to the 2 that are being multiplied here. Because we're just, basically the exponent is telling you how many times something is multiplied. And so we can use addition to figure out how many times something is multiplied. Right? But notice that's just the definition. All I did was rewrite x to the third as 3 x's, rewrite x squared as 2 x's, and then I end up with 5 x's down here on the bottom. And we can see that I just added those 3 to these 3, even though I was multiplying. So the language sometimes gets a little dicey here because we keep saying add when we're multiplying. But what we're doing is we're adding the exponents as a shortcut to multiplication. Okay, so that's our first rule. And let's do this. Go ahead and get rid of that. And we'll take a look at the next one. Okay, so the next one is also born out of the definition. And it's really about what happens when you take something that, in fact, let me write this the other way. I'm going to give this an exponent of 2. And if I decide to raise this to the third power, well, if we think about the definition, what it's actually doing is this 3 up here is telling us to take this x squared and multiply it by itself 3 times. So I have x squared times x squared times x squared. And I'm writing this out longhand so you can see what's actually going on. You usually do this a lot faster than this. But if you notice, if I follow the last rule I just learned, what I would do here is add these exponents together. So this would be x to the 2 plus 2 plus 2. Well, if I add 2 to itself 3 times, that's the same as 3 times 2. So that's x to the 6th. Now, when you're working these out, you don't have to go through all those steps. What I'm doing is showing why it's multiplication. And it's because multiplication is repeated addition, right? And so if I'm multiplying these squared bases over and over again, I'm going to be adding the exponents over and over again. And so it's easier to denote that with multiplication. And so what this ends up boiling down to is if I have x to the m and I raise that to the nth power, I get x to the m times n. Now you notice the difference here between these two rules. The first one says we need to add if we're multiplying like bases. But if I'm raising a power to a higher power, then excuse me, then we multiply the exponents. Okay, now the next one, hopefully it's a little bit intuitive. There's a few different ways to explain it. I like to look at the intuitive explanation first. And the intuitive explanation, when you're looking at something like this, if I'm dividing x to the m over x to the n, well, here's the gut feeling part of this. Okay, so you want to be thinking, well, let's see. When I multiplied like bases, I added the exponents. So now I'm dividing like bases. What does it feel like you should be doing with the exponents? And just as a gut feeling, you should be feeling that there's a subtraction involved. And it's absolutely true. There is a subtraction involved. This ends up being x to the m minus n, right? But let's look at why that works. So let's go ahead and start out with, it's right back to the definition is really what it is. So let's put some numbers in here so we can actually play this game. Okay, so if I follow the rule up here, this guy, I should be subtracting 5 minus 3, and what I should get, and I'm just going to write here over the edge. If the rule works, I should be getting x squared, right? So that's our check to see if we can get this same answer using the definition. Now, if I'm using the definition, that means I need to rewrite this as repeated multiplication. So it's x times x times x times x times x. Whew, boy, that's a lot of x's. And I have 3 x's here on the bottom, right? And these guys are being multiplied. Well, this is actually a division. Well, and division will cancel out multiplication as long as it's the same thing. And so you notice I can reduce this just like a fraction. These x's cancel, these x's cancel, and these x's cancel, and look what I'm left with. I have 2 x's, so I'm left with x times x, and that's equal to x squared. And so really, instead of thinking about, what do you call it? And instead of thinking about subtraction, it's almost better to think about cancellation. That when you look at this, I have 3 down here on the bottom. These 3 are going to cancel 3 out of these 5 on the top, right? And if they cancel 3 out of there, there's going to be 2 left over at the end. And if you want to have the picture of that in your head when you're doing it, you're canceling out part of it. It's not so much subtraction, although subtraction describes it well and gives you correct answers. Here's where subtraction runs into a little bit of problem, though. What if I look at it the other way? Let me clear a spot here. There we go. Ooh, a little more than I wanted, but Okay, so what if I ended up with x to the third over x to the fifth? We'll just look at the reciprocal. If I unwind this definition and write it out, right, I can do the exact same thing and I can cancel three of these out. Now, there's always a question, what do I put on the top if everything cancels out? Well, if everything cancels out, there's always a 1 sitting there, okay? So look what we're left with now. I have 1 over 1, 2, x squared. Now, notice too, if I went ahead and used the subtraction, I have x to the 3 minus 5, which is x to the negative 2 power. Now, we haven't talked about negative exponents. We're going to talk about them here shortly. I have a couple more rules to play around with. But yeah, this actually does generate a negative exponent. And it turns out that when you have a negative exponent, it is going to actually be the same answer as that. And we'll talk about what that means here in a few minutes. But this is very peculiar. I've worked out the same problem two different ways, and I have the answer that looks like this when I work it out one way, and it looks like this when I work it out the other way. And since both ways are correct, these two answers must be equal, right? And they are actually equal. 1 over x squared is the same thing as x to the negative 2 power. And if you think about it, and before we even go into the full explanation here, if I have a positive power, it's repeated multiplication. So it kind of makes sense that if I have a negative power, it might be repeated division. And if I divide by x twice, that's the same thing as dividing by x squared. So really, when you have negative exponents, it's describing division. But we'll find a nicer way to take a look at it, and it actually has to do with this. Because it turns out things are a lot easier to compute with when they're positive exponents, but negative exponents have their place, and anyone climbing the ladder of math past this class is going to need it. So let's go ahead and take a look at a couple more rules here and play around with how to deal with them. And then where'd I put it? There it is. Then we'll do a couple of examples, and then we'll introduce the negatives and see how the negatives play into examples. Okay, so the next couple rules here really have to do with how to handle a product of two different bases with exponents, or a quotient of two different bases with exponents. So the next one I want, oops, let's try this again, is going to be x times y to the nth power. Now, if I'm looking at this thing, what actually ends up happening, let's just change n to a number so we can see it. If I have x times y raised to the nth power, let's make it the third power because that's easier to deal with. What that means, definition-wise, is this is x times y times x times y times x times y. And we know with multiplication, you're allowed to change the order. If it's all multiplication, there's no other operations, you can shuffle those guys around, which means I can rewrite it this way, right? Notice I group these together and group these together, which gives me x to the third times y to the third. Now, if I write this whole thing out, you can kind of see it a little better. Oops. If I have xy to the third is equal to x to the third, y to the third, get this out of the way. You notice what's really happening is this exponent is distributing over multiplication. And it is a distributive process. Exponents distribute over multiplication just like multiplication distributes over addition. So yeah, what you can do here is just rewrite this as x to the n, y to the n. And it actually goes in the reverse order too. If sometimes you need this, it just helps. If I have something like this, they have a common exponent. I can actually, and when I say this, I want you to hear it in air quotes, but I'm factoring it and pulling that exponent out. That's a skill that's a trick we're going to need to use as well. Now, the last rule here is what to do with a quotient, right? If I raise a quotient to a power. And let's go ahead and get this off of here. And I think the quotient's actually a little easier to see than even the multiplication. If I have x over y, and I'm going to give it a number so you can see, to the third, this is x over y times x over y times x over y. Well, when you multiply fractions, you multiply straight across. So this is x to the third over y to the third. Right? So it distributes across division as well. So this is x to the n over y to the n. And it actually works the other way too. If you have a fraction, if I had started out with x to the third over y to the third, I can rewrite this as x over y to the third, right? And that's something that's useful to do every once in a while. It'll save a lot of trouble for things. The one that usually gets used, and we're probably going to use it as soon as we start factoring, at some point it'll pop up, where you end up with something like 1 over x to the third, and you're like, oh, only the denominator's cubed. What am I going to do? Well, 1 to the third is still 1, so I can pretend it's a cube and rewrite this as 1 over x to the third, right? Because we get the same answer either way. So it's just a matter of having little tricks, little tools that you can use to solve problems along the way. The tough part is always figuring out which tool you need where. So let's look at a few examples here. And then we'll take a look at the exponents, or excuse me, the negative exponents, and we'll go from there. Okay, so let's say I have something like, I don't know. Let's do this. Let's do 3p squared cube. And I'm going to square this whole thing, and we're going to multiply that by 2p to the third q to the fourth. Let's make that fourth. There we go. I feel like a Jedi with a lisp every time I say fourth. Okay. Now, let's see what we got here. You do kind of have to think order of operations, but you also want to be thinking about what's legal to do. So first of all, you couldn't multiply this 3 times this 2 because I have to square this term first. And when you square, remember it distributes. The 2 has to hit the 3, this p squared, and this q. So it's going to distribute. The easiest thing to forget is to square the whole number here. Because you start thinking, oh, this only works for variables because all the rules we have are written in terms of variables. But one of those variables could very easily be equal to 3, right? Why not? So it still applies. So 3 squared is 9. P squared squared, now it's a power to a power, so I'm multiplying. So that's p to the fourth. And then q to the second power is q squared. Okay, and then over here we still have 2p to the third, p to the third, q to the fourth. Now, once we have it here, right, we don't have any extra exponents to take care of on the outside. We just need to multiply these two expressions. So you can do it one item at a time. So this is how I like to do it. I start with the numbers, right? So I'll start with the 9 and the 2. 9 times 2 is 18. And then p to the fourth times p to the third. Now, those are like bases, so we add the exponents. P to the fourth times p to the third is p to the seventh. And now we have q. I have q to the second times q to the fourth, so that's q to the sixth. I add the exponents. Now, here is the goal each and every time you work on this. You want any numbers They could be fractions, but you want any numbers worked out, fractions reduced. So that's how you take care of the number part of it. With the variables, you want to see each variable show up exactly one time in the expression. And the other thing you want, um, which we're not going to be dealing with that in these first examples, but the other rule is that you don't want any negative exponents when you're done. Now, I do want to hedge that because there's nothing inherently wrong with a negative exponent. In fact, they're quite useful, especially if some of you are heading on up through pre-calculus and calculus and stuff. Negative exponents are great tools for things. But right now, it's just the game. It's getting used to the rules, so we have to have that goal. We need to manipulate the negative exponents to be positive exponents. That's basically what your rule is. So we have all of that. We have all positive exponents, and each variable shows up exactly one time. All right, so let's take a look at another one. There we go. Okay, so let's take this one a little bit further. Let's say I have 18 x to the fourth y squared over, not 6. Make it, oh, I'll just make it 16. There we go. 16x to the 8th y. Okay, so that's what we're looking at here. So now instead of multiplying two things, we're actually looking at a division. Okay, so here's what I like to do. I know this is going to be, I'm going to have to start figuring out whether my answers are on top or on bottom. It's very likely that I'll have a fraction in my answer. So I'm just going to write this fraction bar first. So now looking at this, the first thing I want to tackle is this numerical part, the part that's all numbers. I'm going to treat it exactly like a regular fraction, and I'm just going to reduce it. And it reduces by 2, so this is now 9/8. Right? I just cut each one in half. I have 9/8. Now, that fraction is not going to reduce any further, so I'm done. Now, these, right, the variables, I like to handle one variable at a time. So I'm just going to look at the x's, and if I pull that out, like I'd really rather you do this in your head, but this is what's happening. You just forget about everything else except the variables you're dealing with. So I'm just pulling out this, this x to the fourth over x to the 8th. I'm going to reduce it and then figure out whether it's going to be, whether the leftovers are on top or bottom. So if I do this, let's see, I have 4 on top and 8 on bottom, and these 4 on top are going to cancel 4 out of the bottom. So that means I'm going to have a 1 left on top and x to the fourth on the bottom, which means that the x to the fourth goes here. Now, again, the next one we're going to do without writing it down. We're just going to talk through it. I'd really rather you not have to write all this stuff down. Most of the time, if you understand the process, the arithmetic can be done pretty much in your head. Okay, so with the y's, I have 2 y's on top and 1 y on bottom. So this one on the bottom is going to cancel out one of the ones on the top, leaving 1 y on the top. And so my final answer, I'm just going to write it a little neater here, is 9y over 8x to the fourth. Right? Each variable shows up one time, the fraction's reduced, and I have no negative exponents. All right. So let's take a look at the next one here. We'll do one more, and what was I looking for? Okay, let's switch back to the pen. Yeah, so now let's take a look at this one. Let's say I have 4a to the third b c squared over 2a to the fifth b squared c. Okay, so I just want to walk through this so we can see the whole process from beginning to end. If you're looking at something like this, again, we're probably going to have a fraction. There's no guarantee, so if you end up not using the fraction bar, just erase it. But most of the time you end up with one. So we'll start first with the numbers. So I'm just going to look at 4 over 2 as its own fraction. So 4 over 2 reduces to 2 over 1. I don't need to write the 1 on the bottom. So I'm just going to write a 2 there. And a to the third over a to the fifth. So these three are going to cancel 3 out of that, leaving me, let's see, the leftovers will be on the bottom, and there'll be 2 of them. So that's an a squared on the bottom. Now I've taken care of the a's. Now let's look at the b's. Okay, so b, I have 1b on top and 2b's on bottom. So this 1b on top is going to cancel 1b out of the bottom, leaving me 1b. And then for c, so I'm done with the b's now. For C, I have 2 on top and 1 on bottom. So the 1 on bottom is going to cancel out one of the ones on top, leaving only 1. So we end up with this as our, answer. 2C over A squared B. It's not bad, huh? All right. So let's add this next rule now. So I'm going to get rid of some of these other rules on the side. I'm assuming that you've written them down by this point, but I need the extra board room, I think. Okay, so now this is the new thing, negative exponents. Okay, so I like to introduce it this way. Let's just take a look at a few things and just watch what happens as the exponent drops. All right, so first off, 2 to the third, we know what 2 to the third is. 2 to the third is 8. Then let's drop the exponent by 1. We get 2 squared, and that gives us a 4. Then we have 2 to the first, and 2 to the first is going to be 2. And so here's the first question here. What happened? I'm going to drop the exponent one more time. That makes it a 0. Okay, so 2 to the 0, that's real interesting. What could we do with that? How do you write something that doesn't show up, right? Because it's how do you multiply something by itself 0 times? Well, this is kind of where this definition breaks down a little bit, is at 0 exponents. There is actually a better definition of exponents, but it's a little beyond this class. In any case, what this ends up being, if you take a look at the pattern, right? If I have 2 to the third and I go from 2 to the third to 2 squared, let's look at what happens here. You notice what I'm actually doing is to reduce the exponent by 1, I divide by the base. I'm dividing by 2. And when I reduce the exponent to go here, over here, I'm dividing by 2 again. And so if I keep dividing by 2, we can see the pattern. If I divide this one by 2, I get a 1. And so 2 to the 0 is 1, which is kind of interesting. It actually turns out you can do the same thing no matter what number you're dealing with, right? 3 to the third is 27. 3 squared is 9. 3 to the first is 3, right? We still have the same pattern. If I go from 27 to 9, I'm dividing by the base. From 9 to 3, I'm dividing by the base. So if I have 3 to the 0, I'm going to divide by the base again, and that gives me a 1. And it doesn't matter what the base is, you're always going to be dividing by it to get to that point. And so you're always going to get 1 at 0. And so that's really kind of a new rule. Shouldn't be too new, but yeah, anything to the 0 power is equal to 1. It is not equal to 0. There's one exception, and that's x cannot be equal to 0. This isn't a complete explanation of why, but it helps, right? 0 to the first power is 0. And so that means the base is 0. If I go 0 to the 0, wouldn't I would have to divide by 0 here, right? And so this is I'm going to say undefined. Technically, it's indeterminate. Sorry about my handwriting, but should probably be used to it by now, but you never know. But yeah, that ends up being undefined. Okay, so that's 0 exponents. What if we keep dropping the exponent down, right? We don't have to stop at 0. Let's keep going. What about, oh, there we go. What about 2 to the negative 1? If I just take one more away from 0, shouldn't we be dividing by 2 again? That would make it 1/2. And if I do it again, 2 to the negative 2, I end up with 1/4. And so you notice I'm continually dividing the previous answer in half. What it ends up boiling down to, though, just so we're clear on this, you can see where that pattern, let me just do this, that pattern is headed. It turns out if I have x to the negative n power, it ends up being 1 over x to the n. And what's more, if I have 1 over x to the negative n, that's the same thing as x to the positive n. So I want to point out what's actually happening here. X to the negative n is the same thing as x to the negative n over 1. And this ends up being 1 over x to the n. What just happened was that it crossed the fraction bar, right? There's always a 1 sitting here. So this one is just this one. But the x to the n moved to the bottom, and when it did, the sign of its exponent changed. The reverse is true when it's on the bottom. X to the negative n is equal to x to the n. So what just happened here is a negative exponent went to the top and became a positive exponent. So the way we're going to deal with these when they come up in the problems is we're going to treat those negative exponents like they're variables that are waving little flags that says, hey, I'm on the wrong side of the fraction bar. So you just switch which side of the fraction bar they're on, and you deal with it from there. So let's take a look here. Let's actually do one of these. So let's say I have 5x to the negative 2, y to the third over 10x to the negative 3, y to the negative 5. Okay, so I have 3 negatives in here. Here's how we deal with them. Basically, what I like to do is I start out by turning all the negatives positive by switching what side of the fraction they're on. So I shuffle everybody around first, and then when everybody has positive exponents, I deal with it like a positive exponent problem. So let's see what that actually looks like. So 5 over 10, I'm not going to worry about. You can reduce it right here if you want. This is the sorting step that I'm working on, so I'm just going to focus on sorting. Now, I do this one piece at a time, and I just look at it. X to the negative 2. That has a negative exponent, which means it's on the wrong side of the fraction bar. So I'm going to write x to the positive 2 on the bottom here. And then moving down, x to the negative 3, well, that's a negative exponent, which means it has to cross the fraction bar, move to the top. Okay, so I have the x's taken care of. Now, y to the third, well, that's a positive exponent. I don't need to move that because it's already positive. So I leave it where it is. And then I turn to the denominator again. Y to the negative 5th, well, that is a negative exponent, which means it has to switch sides to the top. Make it y to the positive 5th. Now that I've sorted everybody, I can start looking at what my final answer is going to be. So let's see here. 5 over 10 would be 1/2. X to the third over x squared. Let's see, these 2 on the bottom are going to cancel 2 on the top, and so the leftovers are going to be up top. So I have an x. And then I don't have any cancellation for the y's, right? Because there's no division. It's only multiplication. They're on the same side of the fraction bar, which means I just add the exponents. Y to the 8th. And so if I clean this up a little bit, this is x times y to the 8th over 2. And that's my final answer with this. So notice what we did. we went through, and the first thing we did was we rewrote all the negative exponents as positive exponents by switching what side of the fraction they're on. So we just start with that shuffling, the sorting. Once I have the sorting done, everyone has positive exponents, and so it turns into the previous kind of problem. And once you have a previous kind of problem, well, it's a problem you already know how to solve. Now, granted, this is the introductory steps of this, so maybe you haven't seen this before, but once each new problem is housed in terms of how the old problem works. So if you learn how to do the previous problem, you change one thing, now you know how to do the new problem. Okay, so let's take it a little bit further, because, that's what I do. Yeah, let's see here. How about if I have, let's say, yeah, we can look at stuff like this. What about things like 5 to the negative 3? Because there's going to be times when you need to know what that is equal to, so you can use it in a problem. Well, we actually handle it exactly the same way as we do the other problems, right? You consider it a fraction, and that negative 3 means it's on the wrong side of the fraction bar. So this is now 1 over 5 to the positive 3, which gives me 1 over 125, right? So this totally works out great. If you have a negative exponent, you just switch what side of the fraction bar it's on and that makes it positive, and then you just compute as is. Now, I did that because I wanted to make sure we knew what to do with the next example. Okay, so let's say I have this. 9a to the third, b to the negative 2, c to the 10th, over 6a to the negative 5th, b to the negative 5th, c to the 7th. Okay, so yeah, this one's getting kind of crazy here. And we're going to take this even further now. We're going to raise this whole thing to the negative 3 power, right? Yeah, so we're getting real nutty here. Actually, this is a good chance where we are right now to go ahead and just take a stab at it. So why don't you go ahead and do this? There's actually more than one way to get a hold of the correct answer on this, and I'll go ahead and show you both of them. But go ahead and pause here and see what you can do. Then we'll take a look. Okay, so I'm assuming you've paused here. So the first way I want to work through this is what I call the inside-out method. What I do is I take this inside piece here, right, the whole thing, and I simplify that first, and then I apply the exponent. Right? It's fairly straightforward. So let's just go through this, and we'll just take the inside piece, and we'll simplify as we go. And then we'll go ahead and raise this. Oh, you extortionist. Okay, hold on a second here. Okay, sorry, my cat wanted out. Now, we can kind of reduce as we go also. So 9/6 reduces to 3/2. So I'll put 3 over 2 here. Now, I need to sort out all the negatives first. So a to the third is where it belongs. A to the negative 5th is not. So we're going to move it to the top. And then we have b squared, b to the negative 2 over b to the negative 5. So both of those need to switch. B to the negative 2 will now be on bottom. Oh, it's positive 2 now. Aye. What's with me and my handwriting today? Probably the same thing that's with me and my handwriting every day, I guess. And then b to the 5th goes on the top. And c to the 10th and c to the 7th stay put. Okay, so you notice I just rewrote this so they're all positive exponents. The only thing I haven't computed is that negative 3 exponent on the outside. Now I just go through and simplify everything I can. 3/2 is still 3/2. a to the third times a to the fifth is a to the eighth. B to the fifth over b squared gives me a b to the third on top. And c to the 10th over c to the 7th gives me a c to the third on top. So we can actually do this and center that 2 on the bottom there. Now, the thing we're missing, that negative 3. That negative 3 hits everybody, right? Doesn't matter who they are. So this is 3 to the negative 3. So that's the first one. In fact, let me switch colors here just so it stands out a little better, so it doesn't blend in too much. So this is going to be 3. This is going to be 3 to the negative 3. That's the first distribution. And then a to the negative 24th, because 8 times negative 3 is negative 24. So it's a to the negative 24th, b to the negative 9, c to the negative 9, over 2 to the negative third. Now, I'm running out of room here. I probably shouldn't have written quite so big, but everybody has negative exponents here. Everybody. So the next line is going to be the answer. So I'm going to go ahead and deal with it from here. If we're going to go to the final answer, we can handle things one at a time. 2 to the negative third, well, it's on the wrong side of the fraction bar, so that means it goes to the top. 2 to the third is 8. So that means I have an 8 on the top. 3 to the negative third on top means it's moving to the bottom. And 3 to the third is 27. Now, looking at the rest of this stuff, all I have are the variables. Everybody has a negative exponent, so I'm just going to sort them. So it looks like everyone moves to the bottom. A to the 24th, B to the 9th, C to the 9th. And I'll just move that 8 so it looks a little nicer here in the center. Right? Okay, so that was the inside out method. And it got a little clunky just because that mostly had to do with me running out of space. But yeah, you just basically, the idea is you simplify the inside as much as you can, and then you apply the exponent from the outside. Not so bad. Okay, well, let's go ahead and get rid of this. We see the answer now. Let's see if we can get the same answer computing it the other way. So the other way is outside in. And in this particular case, the outside in is an easier way to do it. Although it does change. Which one's going to be nicer really just depends on the situation, and you're going to figure it out by doing a bunch of them, which one's nicer to use when. Okay, so we know the answer here, so we can check ourselves. Now, so the other way to do this is to distribute this ahead of time before we start sorting the variables. Now, I do want to point out one thing. 9 to the third, you would be computing 9 to the third power, which is a really big number. In fact, let's see, what is that? So 9 to the third, oh my God, I'm not even going to work that out right now. 729, I think it ends up being, but still, it's a big number. It's easier if you reduce the fraction first, right? So that's what I'm going to do kind of here on the side. I'm going to just reduce this, make it a 3, and make that a 2, so I know that I'm applying these exponents to 3's and 2's. All right, so that means I have 3 to the negative 3, a to the negative 9. Now, here's an interesting thing here. I have a negative times a negative. That makes the exponent positive, so that's going to save a little bit. So that means it's b to the positive 6, and then c to the negative 30, and then we'll do the bottom. 2 to the negative 3, and that's a negative times a negative, so that's now a to the positive 15. Let's see here. Where am I? Oh, b to the positive 15, and c to the negative 21. right? So now we have a few negative exponents. We can just sort those out and take care of them now. So let's see, both 2 to the third moves to the top, 3 to the third moves to the bottom, a to the 15 stays put, a to the negative 9 drops to the bottom to make it a to the ninth. The b's stay put, and the c's both switch. So once we have it here, it's just simplifying. 2 to the third is 8. 3 to the third is 27. So far, so good. We're matching. Now, let's see here. A to the 15th times a to the 9. Let's see. 15 plus 9 is 24, so this is a to the 24th. B to the 6th over b to the 15th. The 6 of these are going to cancel out, leaving me b to the 9th. And then here, 21 of these 30 are going to cancel out, leaving me c to the 9th. And you'll notice that completely matches up. Right? So we did the problem two different ways, and the answers match. So now, a lot of this, some of the little nuances and tricks and stuff, it really is just a matter of just trying stuff, because there's most of these have about a dozen different ways that you can do them. I know I like to kind of take it down into the inside out method and outside in method, which the outside in was the one that we just did. But there really are a lot of different ways to do it. And as long as you are applying the rules correctly, you should come up with the correct answer eventually. So in any case, that concludes everything I wanted to talk about here. And so until next time, keep your wits and your pencils sharp.